Thank you all for coming. And I'm really excited to be here and excited to be talking to you. And what I want to talk to you about today is what, from my perspective, is the answer to the question that you see on the screen. What's the next big thing that's going to happen in nanotech? Now, one thing I think we can all agree on, what was the last big thing to happen in nanotech? And that was, of course, the information revolution. And most of the people in this room, their jobs are a direct consequence of the things that happened in the information revolution. However, if we're looking for the next big thing, there's something that we have to keep in mind, that almost nobody saw this thing coming. If you would have had this conference in the 50s and asked people what the next big thing was, they would have said atomic airplanes or something like that. Most people missed what was coming. But not everyone. A few people got it right. For example, if you're a physicist, you're in love with Richard Feynman for getting it right. Richard Feynman gave a talk in Pasadena in '59 called "There's Plenty of Room at the Bottom," where he hit a lot of the major highlights and did it in a very clear and concise way. Now, we should be a little bit worried, however, because we're talking about technology, and Feynman was a physicist. And physicists have a very strange relationship to technology, which is illustrated here. So imagine technology were a cow. Okay, so that's what technology is. This is what a physicist would view technology as. So we take away all the unimportant parts of a cow, and we leave behind what's really cow, the essence of cowness, which is that it has spots and it goes moo. But it's worse than this, because a physicist, when presented with something like a cow, will immediately try to push it to its limits. For example, here's a quote. I think here's a quote. There it is. Physicists tell us that the fastest animal on Earth with a speed of 120 feet per second is a cow that has been dropped out of a helicopter. So this is what we like to do with technology, is think about what happens if you push it to its absolute limits. And in essence, that's what Feynman did in his talk. And if you go read the thing and see what he actually said, he said two things which are, we know about, which is he said we're going to miniaturize information and we're going to miniaturize computing. And those two things, and it was already happening, by the way. In a certain sense, Feynman was just reporting on the events that were happening in Silicon Valley at that time. But this wasn't all Feynman said. He didn't just say we were going to miniaturize information and computing. He said we were going to miniaturize machines. There was nothing stopping us from taking all the kind of macro-scale machines around us and making them in ultra-miniature form. And in fact, we haven't really done that yet. We're starting, but it's just beginning. It's in the very early days of the miniaturization of machine movement. And I think Feynman got this one right, too. I think the next big thing is going to be miniaturized machines and interfaces. Or maybe more correctly, one of the next big things is going to be miniaturized machines and interfaces. And I've added interfaces to this because I wanted to include certain things. Anything that can gather info and or manipulate the environment at the milli, micro, or nano scale, I'm including in the category of what I'm talking about here today. So first I'm going to say a little bit about this in general, and then I'm going to focus in on nano in specific. And the first thing I'd like to say is, well, I think everybody knows this. Of course, miniaturization is important. Everywhere you look, you see people making little tiny helicopters, little bugs that know how to fly around. MEMS as a field has been around for a couple of decades. It's by no means new. Techniques, for example, to manipulate and read information out of DNA have led to revolutions in biomedicine. Getting nanoscale machines and interfaces small is by no means a revolutionary idea. It's widely in practice. But it's still in the very early days. And for example, to illustrate that, if you take your iPhone, it's mostly electronics. It's mostly information processing. But there's a little bit of machine in it. For example, there's a MEMS accelerometer and a gyroscope inside of your phone. And those two little machines dramatically change the way you relate to your phone. It knows if it's up or down or what's happening to it, and so it begins to be an object that interacts with its environment in a much different way. It's not just an abstract information processor, it's starting to live in its world. It gives, this sort of machines and interfaces technology starts to give systems situational awareness. They know what's going on around them, and it completely changes our relationship to technology. So I think this is going to be huge. And why hasn't it happened yet? Well, first off, it's a much harder problem. And to make that clear, information is basically, the size of information is irrelevant. It's just information. You make it smaller, you just can pack it more densely. And furthermore, the technologies for manipulating information are also, at least we have been for 50 years, scale invariant. First you make the transistors bigger, then you make them smaller, then you make them smaller still. For the information technology world, we had Moore's law. You had to get innovative right at the beginning, invent the transistor, and then from then on, it's just in a matter of execution. This is not to say there weren't enormous technological problems to be solved at executing Moore's law, but in a certain sense, it's easy in that you just have to keep doing the same thing better. Now, information is very different than when you're trying to think about machines and interfaces, because there, size matters in a very, very dramatic way. It's not scale invariant. And by that, I mean if you want to build a robot fly, for example, you have to understand aerodynamics at the millimeter scale. If you want to make a circuit that reads neurons, it's got to be the right size to read a neuron. It's got to be 10 microns in size. If you want to extract information from DNA, you can't make a big version first. You have to go in and make something that knows how to interact with DNA on DNA's terms. So that means size must match the system that you care about. And it also is very important that the physics is different at each of these size scales. So what you learn when you're thinking about making artificial flies won't necessarily help you to do better DNA technology. And so it's a much harder problem. It's a much more diverse problem than the information technology problem. And in particular, I will say that small machines and interfaces, unlike infotech, is going to be is and will continue to be a very heterogeneous kind of technology with many overlapping ways of going about it, and that will operate in very different niches. So there'll be a lot of small players and not just one or two big players. That's my expectation, which is, I think, kind of exciting and interesting. It means that there's a lot more room to play around and for different people to take different approaches to the problem and make some progress without getting killed by the silicon monster. The other thing that's kind of interesting about this technology is it's not happening in this we'll make it big and then shrink it down kind of approach. Things are going on at the milliscale now, things are going on at the microscale now, and also things are going on at the nanoscale all at the same time. These technologies are marching forward in parallel, not in this funnel kind of approach. And you'll notice I didn't draw anything in the little nano circle over here, because that's what I'm going to be talking about basically for the rest of this talk. What is the state of the art for nanotechnology machines and information harvesting machines? Okay, so let me zoom back out a second and say there are really two things that you can legitimately call a nanotechnology that are out there now. The first is the information technology that we've been talking about, and then the second one is life, okay? And life, I should say, is a pretty remarkable technology. And just to, I'm just going to play a few seconds of this video that was made by folks at Harvard University that gives you a glimpse inside of what's inside of a cell. This is not only an information technology, it is most definitely a machine technology. There's stuff down there at the nanometer scale doing all kinds of crazy things that, as a nanotechnologist, I can only dream we were able to do. I mean, it's just ridiculous what's happening inside of every one of the cells inside of your body. And it so far exceeds anything that we know how to do that it boggles the mind. And in that regard, I think learning how to build a machines and interfaces technology that approaches the abilities of this is a 50-year problem. It's a huge long-term problem. But fortunately, there's lots of short-term stuff to gain along the way. Okay, so that's what we would like. How do we get there? Well, one approach, and in fact the approach that's probably been the most successful so far, is to not build a new one. It's just to basically hack life. Okay, if we want a nanotechnology, the heck with it, we'll just use the one we've got, we'll just take control of it. And in fact, if you look at DNA sequencing, for example, which has been a revolutionary technology with its own version of Moore's law over the last decade or so, where the cost of sequencing a human genome has gone from billions to thousands and is on its way to hundreds, really, we're hacking biological technology to a large part. For example, RNA polymerase might be in there duplicating DNA, and we've developed fluorescent techniques to listen in on that process and hear it as it's doing it, or really see it as it's doing its motions, and that's what we use to sequence the genome. We're listening in on biological machinery. Similarly, the field of synthetic biology is, quite literally hacking into a cell. You just write a new set of code and shove it into a cell, and off you go. And similarly, these fun kind of technologies like DNA origami You take a DNA molecule and you make it into some form that will fold up into a nice shape, in this case a set of happy faces, for example. And again, you're just hacking this technology that already existed. And so, at one level, this is great. But at another level, it's both unsatisfying and has drawbacks. And in particular, it's sort of the moral equivalent of, instead of building a tractor, we're just going to find some large animals and hook stuff to them and let them plow our fields. That's basically the state of the art for nanotech now. But it has its issues. It's slow, they're unreliable, and sometimes they have their own agendas, these machines that we harness. And I think in the case of synthetic biology, that's a particular concern. The silly thing, you tell it to build something, and it may decide to evolve and do something else. So we still really would like to do the thing that I told you about, to build a real nanotechnology. But having said that, when we build that nanotechnology, we don't want to give up all the great stuff that we had in electronics. We would still like the kind of computing speed, the robustness, everything that you've had in that world, you would like to carry forth to a real nanoscale technology. And the question is, how do we get there?